Hi everyone, and welcome to the first of two videos on exponential functions. In this lesson we're going to learn about the graphs and some transformations, and then in the next video we're going to actually look at in more detail about how these can be applied to real life scenarios. So what you can expect to learn in this class is what an exponential function is, the shape of an exponential graph, and then we're going to look at two transformations of exponential graphs. So what is an exponential function? Any function in the form f of x equals a to the power of x, where a is just some positive real number, that is called an exponential function. So for example, if you had a function f of x equals 2 to the power of x, that's an exponential function. The thing that's changing, the variable, is the exponent. So the powers are changing, and that's what's driving the function. You could also have something like 10 to the power of x, or half to the power of x. These are all examples of exponential functions. The function f of x equals e to the power of x is a special exponential function where e is the real number 2.718 corrected 3 decimal places. So e is one of those really important numbers like pi, so it doesn't actually ever end. It's an irrational number, it goes on forever. And just the same way that pi is really useful for circles, e is really useful for change, how things might change. So just be aware that we're going to see this quite often when it comes to exponential functions. Okay, so what we're going to do now is we're going to have a look at two functions. So the first one I'm going to have a look at is f of x equals 2 to the power of x. So it's an exponential function where the base is 2. And we're going to have a look at another function, g of x, equals 3 to the power of x. So again, a different exponential function where the base is 3. When it comes to doing this yourself, you can use the table function on the Casio calculator to fill out the tables. But I want to take time to actually fill it out so you can see how the numbers actually behave. You actually kind of learn a lot from just spotting the pattern. So to start off with, x equals minus 2. Well, if I sub that into the function f of x, that's going to give me 2 to the power of minus 2. And from our index laws, we know that that is the same as 2 to the power of 2 to the power of minus 1. And that minus 1 gives us a reciprocal, so we end up with 1/4. Okay, so the next one, x equals minus 1. So that means that we've got f of minus 1 is 2 to the power of minus 1, which is a half. Okay, the next thing then, when x equals 0, that means that f of 0 is 2 to the power of 0. And as we know from our index laws, anything to the power of 0 is 1. Then the next thing we're going to have a look at is x equals 1. So that leaves us with 2 to the power of 1, which is simply 2. Then x equals 2. So that's 2 squared, which is 4. And we can keep this going and you'll get 8, 16, 32. Okay. So likewise then, if we have a look at the other function, starting on with x equals minus 2, g of minus 2 is 3 to the power of minus 2, which is 1 over 3 squared, which is 1 over 9. So we have 1 over 9, 1 over 3, 1, 3, 9, 27, 81, and 243. So now that we have those tables filled out, I'm going to plot them onto the graph. We're going to have a look at the behavior of the function. So at minus 2, we have a value of 1/4, which is quite low, and it's going to be quite hard to see on my graph. It's going to be quite close to 0, unfortunately. And then at minus 1, we have half, so a little bit bigger. And at 0, we have 1. So on the y-axis, we're crossing at 1. At 1, we have a value of 2. At 2, we're going to have a value of 4. At 3, we have a value of 8. So the points are getting gradually bigger now. And then at 4, we're going to take a jump to 16. And at 5, you're going to take a bigger jump to 32. If I were actually to work out f of 6, I wouldn't have enough space on this graph because the value would be 64. So you can see that it starts off quite slowly, that there is just a small amount of growth at the start, but then the growth starts to kind of really become quite rapid. Okay, so it will continue on like that, and I actually wouldn't be able to plot the next one on my graph. F of 6, so 2 to the power 6 is 64, so I actually wouldn't have enough space on this graph. So that's f of x, so I'm just going to label that f of x, and I'm going to move on now to g of x, so 3 to the power of x. So this one starts at minus 2, 1 over 9. So again, starting off really low there. Because my scale is so small, that looks like it's really close to 0, even though we know that it's not. Then at minus 1, we have a third, so slightly above a half on the last one. Then the next one is going to cross at 1, okay? So that's the thing both graphs have in common, is that they are going to cross the y-axis at 0, 1, okay? So the y-intercept for all of these graphs is 0, 1, okay? So the next thing is 1 is 3. Then g of 2 is going to give us 9. Then g of 3 gives us 27. So you can see this is rising a lot quicker, and that's because the base is bigger. So that gives us 27. The next one I actually can't fit on this graph because I just don't have the space. And likewise g of 5, I won't be able to fit it on. So I'm going to sketch what we've got. Excuse me, I'll have to erase that. I'm going to sketch what we've got, and then we're going to take some notes about the features of the graphs. And label that g of x. Okay, so it might be a little bit more useful to see them plotted on Desmos, as it might be a little bit quicker and easier to follow than my scrolls. So we had a look at 2 to the power of x, which was that function. You can see how quickly that rises. Okay, so it just kind of goes off the chart quite quickly. It rises really slowly at the start, but you can see a huge amount of progress thereafter. Another thing to notice is that it never becomes below the x-axis. So you will always have a value of above 0. Okay, so it'll never be 0. It's always above 0. Okay, so that's 2 to the power of x. If we have a look at 3 to the power of x, is similar. It rises really, really quickly. This one rises more quickly. Okay, so likewise you can predict that if you had something like 10 to the power of x, that's going to rise an awful lot quicker again. Okay, so something to notice is, what if you've just got 1 to the power of x? Well, you're just going to have a flat line, because 1 to the power of 1 is the same as 1 to the power of 2, which is the same as 1 to the power of 3. You're just going to have 1 basically. Okay, so that's how those graphs look. I'd like to just maybe focus in on a few important points. So as you can see there, they always pass through at the coordinate 0, 1. Okay, so our y-intercept is going to be 0, 1. The other thing worth noting is what happens when you've got to the power of 1. So if you have a look at the green graph there, that was 2 to the power of x. At 1, you have a value of 2. For 3 to the power of x, which is the purple graph, at 1, you've got a value of 3. So 3 to the power of 1 is 3. And then at the black graph at 1, which is 10 to the power of x, you will have 10. So when you have a look at a function, you should always be able to predict those two coordinates. So the coordinate where x is equal to 0 and the coordinate where x is equal to 1. So as I mentioned in the previous slide, if your base is 1, you're not actually going to see that rise because there will be no change. But I just wanted to show you a graph that's actually quite close to 1. So 1.01 to the power of x. So you can see, judging by the numbers on the x-axis, like it does take quite a while to see that exponential growth, but it is there. So for any number greater than 1, you are going to see exponential growth. And this graph here should remind you of some that we've seen in the news recently. So if you have a look at the next slide, you can see here that this is the total cases of COVID-19 outside of China. And you can see the relationship between the two graphs very clearly. So when it comes to the growth of viruses or the movement of viruses, you can actually model that using exponential functions. They're really, really useful, and they'll probably be used as part of the ongoing crisis to make predictions and to make decisions. So as you can see, there was very few cases until around, say, February 24th, and you can see a dramatic rise from there, similar to how you would have seen it in the 1.01 to the power of x graph. So they will try to manage that base, I suppose, to keep it as low as possible so that the rise is not as high or as dramatic as it could be. Okay, so just to summarize what we've learned so far, this is the general shape of the exponential graph. All graphs of the form y equals a to the power of x intersect at the y-axis at 0, 1. Now, there is actually a case we've overlooked. I've discussed what happens when it's 1, I've discussed what happens when it's greater than 1, but what we haven't looked at yet is where the base, a, is between 1 and 0. So we're talking about numbers like a half, 0.1, anything between 0 and 1. What does that look like?